Hello. Yeah, so good evening, everyone. So last class we have almost completed with inequalities, even some of the advanced ones like the holders inequality. I guess I haven't discussed Minkowski's inequality. Well, I said Minkowski's inequality was the generalization of triangular inequality. So we have covered Minkowski, right? So we have covered Minkowski and Holder. And Young's inequality is the pretty specific case of Holder. Also T2's inequality. Okay. And Cauchy-Schwarz, Nestet, Chebyshev, Janssen rearrangement, and the AMGM inequalities. Right. So now let's practice some problems from Tomato. So Tomato short answer type. Okay, let's start with this one. It's question 118. So So the question is, so n is an integer greater than 2, you have to show n factorial square of that is greater than n power n. So this is the question. As always, let's try and see smaller examples. So for n equals to, so we can't take 2, so let's take 3. This gives n factorial squared is equals to 3 factorial squared, which is 6 squared or 36. And 3 power n power n is 3 power 3, which is in this case 27. So 27 is indeed smaller than 36. So it holds. So yeah, it looks like a very obvious induction problem. So, so let's try to apply induction. So the base case is this, and it's already done. Now induction hypothesis, assume n power n factorial squared is greater than n power n for all n inside not 1, 3, 4, 5 up till k. Right. So yeah, so now we want to show n plus or k plus 1 factorial squared is greater than k plus 1 power k plus 1. So let's just multiply. So we have k factorial squared is greater than k power k. If we multiply k plus 1 squared both sides, so we get this on the right hand side. is k power k is squared plus so we want k plus 1 power k plus 1, right? So let's see what k plus 1 power k plus 1 can be written as. Can be written as k plus 1. If we use binomial, we get k power k plus 1 plus k power k times k plus 1 c1 plus up to 1. So this is k power k plus 1, k power k plus 1. So that's 2k power k plus 1 plus k power k plus dot 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 till 1. So you can see this 2ab term is cancelling out along with k power k. Now I have to somehow show that the rest of the terms are indeed smaller than 2 k power k 2 plus k. So how to show that? So enough to show k power k plus 2 greater than or equals to k plus 1 c2 k power k minus 1 plus dot 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 till 1. So So we can think of it like this. Each of these terms on the right, so they are of the form k plus 1 sum I times k power k minus 1 minus I, where I runs from or k minus I plus 1. I runs from 2 to 2 to k plus 1. Right, so putting k equals I equals to 2, we get the first term, k plus 1 c2 times k power k minus 1. All right, so next, okay, we can, so we have to bound these somehow. So a very crude bound can be like k like we know NC2 are, okay. So each of these terms from the k plus 1 ci, so we can get like at most I fact, like we can think of it as we are getting I factors of something of the order of k. So k plus 1, k minus 1, like that up to k minus 1 plus k minus I plus 1. So we are getting I things. And from k power k minus I plus 1, we are getting the rest of k minus I plus 1 things. So all of them are, we can think of it as the order of k, although the trailing factors are quite smaller than k, and they will tend towards 1 as I increases. So we can say all the terms here are less than or equal to k power I, and all the terms here are already equal to k power k minus I plus 1. So their product is less than or equal to k power k plus 1. So we can say this is less than or equal to sum over I runs from 2 to k plus 1, each of them less than k power k plus 1. So 2 to k plus 1, there are k minus 1 many things. So we can roughly think of it as k many things. Actually, k many things are larger than k minus 1 many things. So it's k power k plus 2. So we can show this inequality like this. And that should be enough for proving the induction. Therefore, by principle of mathematical induction, I guess the variable was n. N factor square is indeed greater than n power n. Well, there is another way, a much simpler one to prove this. I guess I should have come up with that first. So method 2. So we can write so we can see n minus I. This is less than I into n minus I. Obviously, since I is greater than or equal to 1. Right. So next, what we can do is we can take a product over I. So taking product of I from 2 to n. Okay, before taking product, let's bring I onto the right. So I plus I times n minus I, which if we take common I, it's n plus 1 minus I. Now taking product, I runs from 2 to n. I runs from 2 to n. Now the left hand side is n power n minus 1, I guess. Right, so n minus 2 plus 1, n minus 1. And the right hand side is, we can break the product as so the product is like I will go from 2 to n, and why am I making it from 2? Let's do it from 1. So 1 to n, right? So if I make it from 1, I won't be able to. Okay, the inequality is already there, right? Okay. So the left hand side is n power n, and I can break it into two halves. And now I can just rename it, like do a change of variables. So let j be equals to n plus 1 minus I. Therefore, n power n less than product over 1 to n I times product over j equals to 1 to n j. And these products, we know they're just n factorial and n factorial. So n factor squared. And we directly get the inequality without any induction or any iterative arguments. Any doubts? If not, so let's move on to the next problem. So this is problem number 80. So it says if A, B, C are positive numbers and okay, nothing else, I can show that B squared plus C squared over B plus C squared plus A squared over C plus A plus A squared plus B squared over A plus B is greater than or equal to their sum, A plus B plus C. So what about this one? We have three positive numbers, so we are free to use AMGM Cauchy since they only work with positive integers. I mean, positive reals, not integers, not necessarily integers. So whenever you you read any condition involving positive reals, do give AMGM a thought. So I guess I should give you 5 minutes to think about it. So yeah, take 5 minutes. Okay, so I'm back. So where is my pens? So as I suggested, we should first try to apply AMGM or the extended family AMGM, QM, HM. So if we are able to show each of these terms are correspondingly greater than a plus b by 2, since putting a equals to b, we get a plus b squared by a plus b. So it's like a plus b whole squared minus 2ab by a plus b, which is, if we put a equals to b, it's 4b squared minus 2b squared by 2b. That's 2b squared by 2b, which is b. And in this case too, we get a plus b, which is 2b by b by 2 is 2, is b. So we have got a chance to make this the lower bound. So suppose you take the vector ab. These are the observations, and you also take the weights as a and b, and then the arithmetic mean, the weighted am is a times a plus b times b by a plus b, which is each term on the left hand side. Now if you use GM, it would be a power a times b power b whole to the power 1 by a plus b. And that doesn't quite equate a plus b by 2. So instead, if you use the harmonic mean, so the weighted harmonic mean is a plus b by a times 1 by a plus b times 1 by b. That's exactly what we're looking for, a plus b by 2. Yeah, so we have to use AMHM inequality. So therefore, a squared plus b squared by a plus b greater than a plus b by 2, and b squared plus c squared b plus c greater than b plus c by 2, and c squared plus a squared by hc plus c greater than c plus a by 2. Adding those all up, we get the required result. So we get it right. So that was easy too. Next. Okay, try problem 79. Question 79. So it says that theta i's, so theta 1, theta 2, theta 3 up till theta 10, be any values in the closed interval 0 to pi, then show that f equals 1 plus sine squared theta 1 times 1 plus cos squared theta 2 times 1 plus sine squared theta 2. Okay, plus 1. Okay, they're alternating, right? Like that. Up till 1 plus sine squared theta 10. 1 plus cos squared theta 10. Okay, so let me bring it to the left as I'm running out of space. Yeah, so this thing has to be shown to be less than 9 by 4 power 10. And okay, the part question is what's the maximum value attained by f, and at what values of theta 1, theta 2 up to theta 10 is the maximum value attained. Okay. So there are 10 angles, and the power is also 10. That kind of hints us at using some form of term-wise inequality, right? So let's pair up the terms with corresponding ratios of sine and cosine. Suppose we take the first two. So what's the maximum value? Well, at pi by 4, so at pi by 4, sorry, theta 1 equals to pi by 4. This thing is 1 plus half times 1 plus half. That's 9 by 4. So already got the upper bound. The upper bound is achievable. Therefore, so theta is have no restrictions, right, other than being in the interval 0 to pi. So we can set all pi i's, pi I equal to pi by 4 for all I in 1 to 10. That implies f at pi by 4 is 9 by 4 power 10. So the upper bound is attended. The next inequality. So so we have cos square 1 plus sine square 1 equals to cos square x plus sine square x equals to 1, right? So we can try to use EMGM maybe. So 1 plus sine square theta 1, theta I plus 1 plus, so plus 1 plus cos squared theta I by 2. This is greater than or equal to square root of sine squared theta I cos squared theta I. Squaring both sides. Our expression actually comes on the right. So two we can manage. So it's 1 plus sine squared theta I plus cos squared theta I, which is another 1. So we get 9 by 4. So we can take the product over theta I is from I from 1 through 10, I from 1 through 10, which is f. So f has the upper bound, which is the tens, at 5 by 4, 9 by 4 power 10. Right, so I hope this was also clear. It's quite easy, right? Anything? Okay, let's look at this log example. So it says if you have a, b, c greater than 1, and so you have to find the minimum value for log bc base a plus log ca base b plus log ac base, ab base c. So what's the minimum value of this? Okay. So you can take this as big A, this is big B, and this as big C. So I have to find the lower bound for A plus B plus C. And we know or maybe we should instead so let's first break it further down. So log BC base A is log B base A plus log C base A plus log C base B plus log A base B plus log A base C times, plus log B base C. That is equal to log B by log A, log C by log A, log C by log B, and log A by log B. Log A by log C, log B by log C. So there are three. Oh, all the terms are distinct. Okay. So now we can take log A as capital A, log B as capital B, and log C as capital C. So it's A by B plus, sorry, I guess I should write them in order. B by A plus C by A, C by B plus A by B, A by C plus B by C. So you can clearly use AMGM here, right? So that's greater than or equal to 6 times 1 by 6th root of the product, which is just 1. You mean they cancel out, right? So it's 1. So it's bounded below by 6. So the minimum value is 6. So where is the equality attained? It's attained when A equals to B equals to C. I mean, capital A is equals to capital B equals to capital C. So that just implies the logs are also equal. Okay, this one is interesting. Start. So this is BStat 2010. This is a subjective paper. Question number 7. So we have a paper, a rectangular sheet of paper measuring 7 by 3 centimeters. And a corner of it is folded in a way such that the corner meets the opposite sides along the length. So one of the corners is getting folded. Something like this. So consider a rectangular sheet of paper ABCD. Suppose B dash and D dash are 2 points on AB and AD. Okay. B dash and D dash. Right, so they're 2 points respectively on AB and AD respectively, such that if the paper is folded along B dash D dash line, the 2 points, and then B dash D dash, okay, folded along B dash D dash, then A falls on A dash on the side DC. On the side DC. Okay. But I guess I drew the picture wrong. So the longer side is AB and AD is the shorter one. So this is A dash. Sorry, the corner. This is A dash. This is B dash D dash. So we need to find the maximum area of the triangle formed with the crease as the hypotenuse. So you have to find the maximum area of this triangle. Sorry for my bad illustration, but this is basically a mirror. These two halves should be identical. So apparently we have a squared and a line which just intersects it. So the first, okay, we have to write some equation and maximize it. If we draw a line like this is perpendicular. This is where A dash meets the other edge. Sorry, other edge. So let's take this as x. Take this as x. So this is 7 minus x. And we can take one of them as theta. This is theta. Remember, this is perpendicular, so this is so we're trying to find the perpendicular with the help of our base. So 7 tan theta. Sorry, 7 minus x tan theta. That's 7 minus x. This is 7 minus x tan theta. So the area is 7 minus x squared tan theta by 2. So what theta and x can't be independent, right? So to bring it down to one variable. So we have 3 for that relation. So this length over here is 3. Okay, so we know 7 minus x tan theta plus so we took this as theta, so that means this is also theta. This is theta dash. This is theta, so this is also theta. So you see theta plus theta dash is equals to 90. Yeah, that's obvious since theta and theta dash by definition is 90 minus theta. What else is there? Mm, so this is theta dash. This is theta dash. And this is therefore 2 pi minus 2 theta dash. That is pi minus twice of pi by 2 minus theta. That is, pi by 2 minus theta by 2. So that is 2 theta. So this is 2 theta. This internal angle. So if I call this triangle, can't call it. We already have names. So this is 2 theta. Therefore, in triangle D dash A, D dash A dash, we know this side is 7 minus x tan theta. And this side is 3 minus that. Call it y. Let's call this y. This is 3 minus y. So we have hypotenuse. Hypotenuse by perpendicular. No, sorry, base is cos 2 theta. So using dividendo, we get or just reverse it. 1 by cos 2 theta. And okay, sorry. Just subtract 1 from, so this is 3 by 3 minus y. So it's, so you're adding 1. So 1 plus cos 2 theta, which is 2 cos squared theta. Cos squared theta. That's 3 by 3 minus y. So 3 by 3 minus y is okay. We don't need further simplification, just we need delta. So delta is 7 minus x squared tan theta by 2. We know x is, so y is, where is y? So y is 3 minus 7 minus x tan theta. Three gets cancelled. It's 3 by 7 minus x tan theta. Putting it here, we get, okay, so this is cos squared theta. So finally, we get an equation with theta and x, so we can eliminate one of them. Okay, let's decide and eliminate theta. So 7 minus x is 1 by 2 cos squared theta times tan theta 3. So here we have 3 by 2 cos squared theta tan theta times tan theta. Tan theta gets cancelled. We have 3 by 2 cos squared theta. Oh, sorry, so we had squared. So we had 7 minus x squared. Sorry. So it's 9 by 2 cos 4 theta tan squared theta times, so there is a 2 here also, tan theta. So this 2 actually turns 4. Sorry for that. So 1 tan theta out. We have 9 by 16, 1 by cos 4 theta. Tan theta. So that's cos cube theta sin theta. You have to find the maximum value, right? Or was it the minimum value? No, the maximum value, right? So how to find the maximum value? So to find the maximum value, can we use AMGM? Let's see. So we can say, so we can take this as the geometric mean or the weighted geometric mean. So we get cos theta twice cos theta plus sin theta. So we have to take by 2 by 2. Okay. So we know cos squared theta plus sin squared theta is 1. Right. So we can take 3 by 2 times 2 by 3 cos squared theta plus 2 times half times 2 sin squared theta is greater than or equal to so you have to divide this by 2. Take power cos squared theta power 2 by 3 cos squared theta power 3 by 2. Yeah. No. Power 2 by 3. Is it 2 by 3? No. So the whole power will be half. So 2 by 3 cos squared theta power 3 by 2 times 2 sin squared theta power half. Whole power 3 by 2 plus 1 by 2, which is 2, I guess. Right. So cos squared theta plus sin squared theta is 1 is greater than or equal to 2 by 3 power 3 by 2 times 2 power half cos cube theta sin theta. This whole thing times 4. So this 2 comes up here and now we are finally taking square on both sides. So that equates to 3 by 2 times root 2 times 4. Sorry. So that's 2 to 4. So 16 by 3 root 3. Cos cube theta sine theta. So cos cube theta sine theta is bounded above by 3 root 3 by 16. So that area is coming to be 16 by 9, or 9 by 16, sorry. 9 by 16, 1 by cos cube theta sine theta, which is greater than or equal to 9 by 16, 16 by 3 root 3. Just root 3. Is that just root 3? So I made a mistake, and this should have been 8. Same here too. So this was 8. So this is 2 root 3. So the smallest value of delta is actually 2 root 3. So what was the question? We had to determine the largest possible value of triangle A, B dash, D dash. So A, B dash, D dash is, yeah, same as this area, right? Okay, try to solve some interesting problems. Not boring inequalities. Right. So it says a particle at time 0 is at a point 0 on the real line, and at time 1 the particle divides into 2 and instantaneously after division, one particle moves 1 unit to the left and the other one moves 1 unit to the right. At time 2, each of these particles divide into 2 again, and one of the 2 particles moves 1 unit to the left and the other moves 1 unit to the right. Whenever 2 particles meet, they destroy each other, leaving nothing behind. So how many particles will be there after 2 power 11 plus 1 time? Okay. So okay, let's draw some figures. So it says there is the question is question number 186. So there is a number line, and at t equals to 0, the particles are at point 0. Okay. Then at every time step, the particle divides into 2, each of them divides into 2, and instantaneously after division, one particle moves 1 unit to the left and the other one moves 1 unit to the right. Okay. So the particle was here, it moved 1, moved 1. Then the next blast happened. This particle got divided into 2. One moved left and one moved right. This particle also collided, exploded, and destroyed the one that was coming from the right. So there are 2 particles at the end of time step 2. Next, again after time step 3, there will be, now there are no particles, just 2 particles here. One here and one here. So if you explode, you get here one, here the other one. Sorry. So this one over here is here. So there are 4 particles at t equals to 3. I mean, yeah, t equals to 3. Next, these destroyed. They left 2 more particles. And these also destroy. They leave 2 more particles. Okay. So you can see a pattern, like at t equals to, what do we start with? So we had 0 particle. Sorry, we had a particle at 0 position on the number line. And t equals to 1, they divided into 2. Right. So t equals to 1, the number of particles were 2. T equals to 2, the number of particles were again 2. At t equals to 3, the number of particles were 4. But at t equals to 4, the number of particles were again 2. So it seems like they are periodically coming to 2. So t equals to 5. They get split, number of particles 4 again. They get destroyed. So number of particles 4 again. Okay, so 0, 1, 2, 3. Two points are always moving apart further and further on. So they have asked for number of particles at 2 power 11 plus 1. So I kind of suspect that number should be 2. Let's see. It seems like at all perfect powers of 2, they are resetting to 2 points. Okay, so then 0, 1, 2, 3, 4. So let's see why there are exactly two particles after 2 power n time. Maybe we can use induction. So our claim is at the end of 2 power n moves, or 2 power n time, we have exactly 2 points, right? So for some k, we have 2 points, right? Let's see what happens from now on. So this is obvious that the extent of the 2 points will be 2 power k plus 1 at this point of time, since the outermost 2 points are always moving away from each other by 2 steps centered at 0. So now at t equals to 2 power k plus 1, this point moves here and here, moves here and here. So we can consider this instance as okay. Okay, so this is the leading edge which is going into collapsing, right? So at time t equals to 2 power k plus uh, oh right. So we can consider each of them as t equals to 1 0 case, right? T equals to 0, there was or t equals to 1, I guess that was called. Yeah, sorry. It's t equals to 2 case. So t equals to 0, there was a 0 particle, 1 particle in this position. 2 power k plus 1, let's shift the origin. So this is 2 power k, not k plus 1. So we know after 2 power k moves, After 2 power k time, there will be exactly two particles, right? So this particle, so this system you can say call it the right system, will have consisted of just the particle at 2 power k plus 2 power k, the particle at 0, and similarly for the left system, there's not enough space, so just a minute. So this was 2 power k. This is 2 power k plus 1, 2 power k, minus 2 power k minus 2 power k plus 1. So after t equals to 2 power k plus 1, this particle, this right system, will have moved from there to there. And similarly, the left system would have moved from minus 2 power k to 0 and minus 2 power k plus 1. And these two particles, the one from the left system and the one from the right system that moved recently to 0, will just destroy each other. These are already not there. They moved out on both directions. So they will be left with just two particles at 2 power k plus 1 and 2 power k plus minus 2 power k plus 1 at time t equals to 2 power k plus 1, p equals to again 2. So that proves our induction. Right. So at 2 power 11, there will be just two particles. So at 2 power 11 plus 1, there will be four particles. Right, so 4 is our answer. Okay. Next. So in how many different ways the faces of a cube can be painted with 6 different colors? So this is a combinatorics problem. I guess the last one was logical reasoning, right? So yeah. So in how many ways? In how many ways can a dice be colored distinctly? So what's meant by distinctly here? So it means if you take a die, if you take two possible colorings of the die, and if you cannot, in any possible allowed physical rotation, translation, transposition, equate the two dice or superimpose one onto the other, then those two colorings are considered distinct. Like, for example, So these two colorings are certainly distinct, since here the red and blue are adjacent color sides, and here they are opposite, right? So that just makes them distinct. So we have to find the number of possible colorings of a die. So we will formally start combinatorics maybe from next week. Today, let's start off with this exercise as an introduction to. I mean, this is not that easy. Okay. Okay, looks like everyone is left, so maybe we should continue next week. Okay, then. I guess I should end the class here. As it is, I'm feeling too sleepy today. I don't know why. Okay, then. Goodbye.